Probability is always a number between 0 and 1, and it's the number of favorable outcomes divided by the number of possible outcomes. The key thing that's crucial is figuring out the number of possible outcomes before you start. So if I said, what's the probability of the sum of your two dice that you roll being 4, you would have to figure out how many dice rolls there are. The first dice could be 6 possibilities, the second dice could be 6 possibilities. So for this problem, the number of possible outcomes are 36 different possible combinations of dice rolls. Having the sum be 4 would mean that I either rolled a 1 and a 3, or a 3 and a 1, or a 2 and a 2. So the number of favorable outcomes is how many times, like count how many times you get what you want. I get a 4 3 times out of the 36 times. So the probability of the sum being 4 is 4 out of 36, or 1/9. If a problem is an AND problem, you can multiply. Like, for example, if I flip a head and I flip another head, I would take 1/2 times 1/2. That's equal to 1/4. The probability of flipping two heads is a 1/4. It's different with cards because you have a known number of cards in a deck, and even though you can multiply the cards, they're conditional probabilities. The probability of drawing a heart out of a deck of cards is 1/4, because 1/4 of the deck is hearts. But if you break that down, it's really more like this: 13 out of the 52 cards are hearts. And if, let's say, I just drew the ace of hearts, then there's only 12 cards left in the deck, and there's only 51 hearts left. So if the first outcome affects the second, you can still multiply the probabilities, but the probabilities change as you go. I'll let you figure that one out on your own. In general, I remember that you multiply when it says and if it says or, you add, but or isn't quite as easy as adding, because you have to pay attention to whether they're disjoint events or not disjoint events. For disjoint events, like let's say for this class, the probability you get an A is 70%, the probability you get a B is 20%, and the probability you get a C is 10%, and there's no possible way you could fail this class because you're such a hard worker. Okay, so then the probability that you get an A or a B, that is right here, 70% plus 20%, that's equal to 90%. Okay, it is not that easy to do if you have the type of problem, so I made this up: pool, no pool, beach house, no beach house. So this 12 right here represents all of the beach houses that also have a pool. I don't know why I'm thinking about summer. Okay, so if I were to add, let's say, the probability that I have a pool or a beach house, in this case, because the events are not disjoint, if I were to take 16, the probability I have a beach house, plus 72, the probability I have a pool, and add them together, my answer is going to be wrong, because 16 includes the beach houses with pools, and 72 includes the pools that are on the beach. Sorry, yeah. And what happened is I've counted the 12. I've counted this number twice. So when the events are not disjoint, I have to subtract off that little part where they overlap, and if I were to do that, I would end up with 86% of the properties either have a pool or a beach house, which I could get actually easier by just doing the opposite of 14. Some of the problems in the book involve tree diagrams, and I want to show you how to make a tree diagram, but how you can always make a tree diagram into a chart. So let's say 70% of kids go to a doctor, 70% of kids who go to a doctor have a fever. Okay, so we're going to go fever is 0.7, and that means that no fever is 0.3. So when you make a tree diagram, you fill in what you know, and then you fill in the opposite of that because of the rule that probabilities add to 100%. Now it says 70% of kids go to a doctor, have a fever, and 30%, that's supposed to say percent right there, 30% of the kids with a fever have a sore throat. So 30% of the kids with a fever have a sore throat, and that means 70% of the kids with a fever don't have a sore throat. Of the kids who don't have a fever, so no fever, 20% have a sore throat, and that means that 80% of those kids don't. Now I stop and I get out my calculator. 30% of 70% is 21%. 70% of 70% is 49%. 30% of 20% is 6%. And 30% of 80% is 24%. And so now I have all of my possibilities: fever with a sore throat, fever, not a sore throat, fever, no fever, sore throat, no fever, no sore throat. But what I want you to do now is take a look at this same problem, because all of the problems in your textbook make a tree out of this kind of problem, and I want to show you how you can do the exact same problem as a chart, and I really believe that the chart is easier. So let's go fever, no fever, sore throat, no sore throat. It says 70% of the kids who go to the doctor have a fever. There's your 70, which means 30 don't have a fever. It says that 30% of the kids with a fever have a sore throat. So you take 30% of 70, 3 times 7 is 21. There's this number. Fill in the 100. It says 20% of the ones who don't have a fever have a sore throat. So I take 20% of 30. That gives me my 6. And now I just go ahead and fill out the rest of the diagram because they all add up to 100%, because that's my rule. This is going to be 49 and 27 and 73 add up to 100. And now what I want you to look at is how hard or easy it is to answer the following question. What is the probability a patient with a sore throat has a fever? If I answer this question in the chart, so I'm looking at patients with sore throats, I'm looking right here. What is the probability a patient with a sore throat has a fever? That is 21 out of 27, and 21 out of 27 comes out to 77%. Now, let's say that I didn't have the chart to look at and I had to answer that same probability problem with a tree. Answering the question, what's the probability a patient with a sore throat has a fever, means you have to take people who have a fever and people who have a sore throat out of all of the people who have sore throats. Yeah, let's spell throat right. All of the people that have sore throats. And that information is not really readily available in the chart. The patients who have fever and a sore throat, that's 21%, but the patients with sore throats are made up of these patients plus these patients, 27%. It's actually the same math, but it's a lot easier to answer that question when you're looking at the chart than when you're looking at the tree diagram. So if you can turn the tree diagram to the chart, it's going to be easier for you. This formula is given in your book as the probability of B given A equals the probability of A and B divided by the probability of B. Now, you can use the tree diagram and the formula, but I would suggest if you can make it into a chart, it will make it easier. One thing students have trouble with is they get mixed up. The students get mixed up the difference between these two questions. This first question, if a student has a sore throat, what's the probability they have a fever, is saying that if a student has a sore throat, it's a probability of having a sore throat on the bottom, because it's out of the kids with sore throats. And so what's the probability to have a fever? So you take the probability of a fever and a sore throat out of the sore throats. In the second scenario, they say if a student has a fever. So in this problem, they're looking out of all of the students who have fevers. What is the probability to have a sore throat? So this is a probability of a sore throat and a fever. Now, in both cases, the top number is the same. Sore throat and fever were 21%. But the bottom number is going to be different. If you remember, I think 70% of the students had fevers, but only 27% of the students had sore throats. And 21 out of 70 was 30%. They gave you this information in the problem. Geometric probabilities, you know the probability, they're independent, and it's a success or failure question. What that means is it could be like, I make a basket, let's say I'm actually fairly decent at this, and the probability I make a basket is 80%, and the problem that I miss the basket is 20%. So I either make it or I miss it. It has to have two options. It can't be like blue eyes, green eyes, brown eyes. It can't be red M&Ms, yellow M&Ms, green M&Ms, blue M&Ms. It can only be success, failure. And it's also a geometric probability if the question says how many until. So how many baskets do I have to make until I miss? So a geometric question might be, what's the probability that Mrs. Auld misses the first basket on her fourth shot? So that would be like, I make a basket, I make a basket, I make another basket, and ouch, I just missed that last one. I multiply those all together and I get the solution. Geometric probability is actually quite easy. You just really do what it says. Like, for example, what's a probability that I miss my first basket in the first 3 shots? So that could be I miss on the first shot, or it could be I make the first basket but I miss on the second shot, or it could be I make the first 2 baskets but I miss on the third shot. So the probability my first miss comes in one of the first 3 shots is 0.16. Binomial probabilities are different. They're still success, failure, you know P, they're independent, but it's out of a total. So in this type of a problem, let's say the probability I make a basket is 80% and the probability that I miss is 20%. What's the probability that in 10 shots I make, let's say I'm a little off, I only make 7 shots. 10 shots I make 7. So we have to figure out how many ways that can happen. That's 10 choose 7. And that would mean I make 7 baskets, so 0.8 to the 7th, and I miss 3 baskets. And that's the binomial probability. This is 10C7 on your calculator. You can also get out your calculator and go second vars binomial PDF and type in 10, 0.8, 7, and it will just do all of the math for you. So if my shooting percentage is 80%, the probability that I make 7 out of 10 shots is 20%. If I wanted to figure out what the probability I make 8 or more shots, that would be the probability that I make 8 shots, or I make 9 shots, or I make 10 shots. And so I would have to add 8 or 9 or 10 together. This would be 0.8, I made 8, times 0.2, I missed 2. This would be 0.8, I made 9.2, I missed 1, 0.8, I made 10, which really means you don't have to worry about this because it can only happen in one way, and you don't have to worry about this either. And so if I figure out that probability, that is 0.677. There's a way to do this on your calculator too in one fell swoop, although it's a little tricky. The CDF button on your calculator is the cumulative probability button, but it only adds up cumulative probabilities from small to big. So I have to think, instead of what's the probability that I make 8 or more shots, I figure out that, well, that's the opposite, that I make 7 or fewer shots. Here's how I type in 7 or fewer shots on my calculator. If I take 1 minus that, I get the opposite of that, which is 8 or more. We actually spend 3 full class days just on the binomial probabilities in AP Statistics, and you guys get it as just sort of part of a section in pre-calc. So it's a little difficult.